Today's video is about when radiation interacts with matter. So first we're going to quickly look at the electromagnetic radiation. And the electromagnetic spectrum is a range of frequencies and wavelengths of electromagnetic radiation. And you can see the electromagnetic spectrum here. And we can see by this diagram that radiation with long wavelengths have low energies. And I remember this by long and low. So you can see as the wavelength increases here, you have a lower frequency here. So long wavelengths mean low frequencies. And you can see the types of radiation we have here. We have gamma rays, X-rays, UV, our visible light spectrum, which we have here. We have our infrared, microwaves, radio waves, and more radio waves. And we know that gamma, X-ray, and higher UV radiation are ionizing radiation. So this top part of the spectrum here, we know are ionizing. And ionizing is typically removing electrons to form ions. So these ionizing radiations mean that ionization happens where we form ions. So what are the types of energy that we'll be looking at? Well, first we have translational. And translational means moving the entire molecule. So this is the molecule as a whole. So we move the entire molecule from one place to another. We have rotational, which is rotating the molecule as a whole. So we're not rotating one bond, we're rotating the whole molecule. We have vibrational, which is the oscillating of bonds, which fluctuates the bond lengths. So as we vibrate bonds, we oscillate them, the bond length fluctuates, so it changes. And then we have electron energy. So this is moving electrons on energy levels. So we know that energy is quantized in electrons. So electron energy is quantized. But actually, all of these energies are also quantized. And this just means that the system can only uptake certain energies. They can't uptake continuous energies. So certain energies can be uptaken to cause these effects. And we know that translational energy, requires the lowest energy radiation. And the electron energy requires the highest energy radiation. So that means the lowest amount of energy is required to translate and move a molecule as a whole, while the highest energy is required for electrons to move around in energy levels. So first we're going to have a look at translational. And what energy is required to move the molecule as a whole? Well, actually, translational requires very low energy radiation. And this is because it doesn't require much energy to move the molecule as a whole. Now, rotational energy. What's the energy required to rotate a molecule? Well, not much energy either is required to rotate an entire molecule. And so we use lower energy radiation to do this. So this could be microwaves. So this is basically saying that when microwaves are fired at matter, the molecules are caused to rotate. So because rotational energy doesn't require as much as other types of energy, we can use microwaves, a lower energy radiation, to rotate the molecule. And then we have vibrational energy. So what's the energy required to vibrate bonds? Well, oscillating bonds actually require high energy radiation, so like infrared. So vibrating our bonds requires higher energy than moving the molecule as a whole and rotating the molecule as a whole. So when infrared radiation is fired at molecules, this causes the bonds in the molecules to oscillate. So our high energy radiation, our infrared, is fired at our molecules, causing vibration, oscillation of the bonds. And this oscillating or vibrating of bonds increases the bond's kinetic energy. And it's this increasing kinetic energy that increases thermal energy. And this causes us to sense infrared radiation as heat. So when infrared radiation is fired at our molecules on our body, this causes their bonds to oscillate, increasing the bond's kinetic energy, increasing their thermal energy, causing us to feel infrared radiation as heat. And then lastly, we have electron energy. So what energy is required to move electrons in energy levels? So to excite electrons to higher energy levels, loads of energy is actually required. So this means that it will have to be UV or visible light to excite these electrons and move them to different energy levels. But it's important to note that within each band of energy, for example, electron energy, translational energy, different energies are used for different bond strengths. And so, for example, higher energy infrared radiation is used to vibrate or oscillate a CF bond than a CBr bond. So because a chlorine-fluorine bond is of a higher energy infrared radiation is used than the infrared radiation used to vibrate a chlorine-bromine bond with a lower bond enthalpy. So what happens when chlorine atoms absorb UV? So there are three possible options when a chlorine molecule absorbs UV radiation. So first, the chlorine molecules just absorb the energy and release it back out, returning to its original state. So you can see that here, the chlorine molecule absorbs this UV, the electrons are excited, but it just absorbs the energy and releases it and returns to its original state. So this happens when a lower energy radiation, so a lower energy UV is absorbed. And chlorine absorbs a range of visible light also. So this is what makes the chlorine gas appear green. Because it's absorbed all the other coloured lights, all the other wavelengths, except for green, this makes chlorine appear green as a green gas, because the only wavelength that reaches our eyes is green, because it's absorbed all the other visible light wavelengths. And the second option for what happens when chlorine atoms absorb UV is photodissociation. So this is a higher energy radiation that breaks the bonding electrons apart, forming chlorine radicals. And radicals are atoms with unpaired electrons. So chlorine has 7 electrons in its outer shell, meaning there are 3 sets of paired electrons and 1 unpaired electron. So this photodissociation, chlorine absorbs UV and the bonding electrons break apart, causing 2 chlorine radicals to be produced. And this requires a higher energy radiation than the releasing of energy. And the third option is high energy photons cause an electron to gain enough energy to leave the molecule, forming a chlorine ion. So this is ionization, as we saw in the first slide. So a high energy photon, so the highest energy compared to the 2 other options. And this high energy photon causes the electron in the chlorine to gain enough energy to leave the molecule as a whole, forming a chlorine ion, as you can see here, a positive chlorine molecule and an electron. And this is ionization.